So to recap, this is the amount of work, either of these, depending upon the units. For a two-step process, what if this was a one-step process? There we go. What if this was a one-step process? And if this was a one-step process, then it would go from a V initial of 4.09 liters, a P initial of 5.94 atmospheres, to a P final equals 1.59 atmospheres, and a V final of 15.31 liters. And the question is, how much work do you get from a one-step process? And work is still minus P times delta V. The P is always the final P. And now it's V final minus V initial. And if we multiply this out, we get 1.59, 1.59 minus, I always forget this part, do the subtraction first, 15.31 minus 4.09 times 1.59 minus, and I get 17.8 minus 17.8 liter atmospheres, and that's the amount of work in a one-step process. Minus 17.8 liter atmospheres, and we could convert that into joules as well. But you can see that in liter atmospheres, the work is not only different, but greater if you take two steps. And the take-home message for this is that the smaller the steps that you do work in, the more work you can get out of a process. There's two other things I will say. One is that if this has direct application to car engines, meaning the smaller piston size, the smaller the amount of basically expansion of the gas. So smaller pistons are more efficient. More pistons that are smaller for the same volume will give you more work. Of course, you have to construct more pistons, which can be more work as well. And this says nothing about power, by the way. Bigger pistons, if you only have 4 pistons and they're bigger, sure, they will be less efficient, but they will also give you more power than 4 smaller pistons. Finally, in the limit that you have an infinite number of infinitely small steps in which you start to involve calculus, which we do not involve calculus at this point in the course, you would get the maximum amount of work. And again, I don't think we're gonna go into that, but so work is at a max for an infinite number of infinitely small steps. And again, that's a very interesting concept. I'm not sure if you've talked about that in your other courses, especially if you've taken any engineering courses, but I think you will. And myself, as a chemical engineer, spent a lot of time integrating over infinite number of infinitely small steps to get the maximum amount of work for a process in that limit. Anyway, there's much more that we could say, many more things about that that I have not thought about in a long time, since I was an undergraduate, more or less, but we'll leave it there.